course, and the video of lecture 3 is now on the playlist, so you can go check out, okay, and watch it if you have time, of course. Okay, so today is our fourth lecture, so we're still in the topics on thermodynamics, okay, and we'll dive deeper into the detail. So if you recall the last time that we did our lecture from last Thursday, what we did was beginning the chapter of thermodynamics by discussing all the key terms, things like the system, surroundings, and the universe. And we also talked about importance and the definition of the state functions. And we also talked about the first law of thermodynamics regarding delta E, or the change in internal energy, and how that relates to the change of heat and work in and out from your system. Okay? And we also discussed the important concepts on the signs in thermodynamics as well. So when the sign of your value is positive, it means that there's something go in relative to your system. But when the sign of your value is negative, then it means that thing has to go out of the system, right? So that was pretty much what we covered from Thursday. So what about today? We'll dive deeper into detail and then talking more about the concept that we just introduced on Thursday, which we call enthalpy. Okay? So let's recap the topic first. So heat of a constant volume process is equivalent to what? That was from the first law, right? So everything is easily derived from the equation of the first law, which is delta E equals Q plus W, right? And also you know the definition of W, which is work, and work here is minus P delta V, right? So for a constant volume heat, it is simply delta E. Right? Why is it delta E anyway? Because for a constant volume process, what is work? For a constant volume process, what's work? Work is zero. In that case, if you recall, why? Because the volume is constant, so it means that delta V is zero. Right? And if you look at the equation of the first law, delta E equals Q plus W, for a process with constant volume, your work is going to be zero, and Q is going to be Q sub V, or heat of a constant volume process, which is equivalent to delta E. Okay, so this is what you should know. And if you don't know, it can be derived rather easily. Okay, now heat of a constant pressure process is equivalent to delta what? Heat of a constant pressure process is a delta what? That was from last lecture. Maybe you remember. Heat of a constant pressure process is equivalent to delta what? Delta G, delta H, delta E, or anything is delta H, right? Because that's what the definition of enthalpy. If you still don't know, if you still confused why can I make this kind of statement, maybe you can go rewatch the video from the previous lecture, which is now on the playlist. Okay, so go check out and clear all these confusions, of course, before our exam. All right? And then the unit kilojoules per mole is per 1 mole of what? Is it per 1 mole of a particular substance in your reaction? Not really, right? We call it per 1 mole of reaction, right? What does this mean? So it means that it is per 1 mole of reaction, or per moles of any substance in the balanced chemical equation, right? That's what we discussed yesterday. So if you have a reaction, for example, something that looks like this, and let's say this reaction has delta H equals to, oops, equals to X kilojoules per mole. It means that the delta H of this reaction is X kilojoules per mole of this reaction, but per how many moles of A? 2 moles, right? Because the stoichiometric coefficient in front of A is 2, right? And this value of delta H is per 1 mole of B, per 2 moles of A, etc. This concerns only the balance equation. Okay? Any questions before we move on? Things will only get harder, it never gets easier. Okay? So maybe you should constantly review all these topics, okay, so that you keep in touch with all the bases of all the lectures that you learn here. I know university can be hard for everyone, right? Especially compared to when you were from high school, and I cannot understand. From high school, you were online for 2 years, and now it's the first year in university, and everything is kind of fast. Oh, homework, exam, all that kind of stuff. It's your first year, maybe you are shocked a little bit, but eventually you'll get used to that. Okay? So if you have any questions, do not really hesitate. Please ask me. Okay? I'll be more than happy to clear your confusions. Okay? Alright. Now, let's take a look at the relationship between delta H and delta E. So I want you to consider this particular reaction. So you see the reaction in the box here is sodium plus water goes to sodium hydroxide and hydrogen gas. Have any of you seen this reaction in the laboratory before? Yes or no? Maybe not, right? Because this reaction is really scary. Okay? Do you know what does it produce? Fire. If you put sodium metal in water, and you of course take the chemistry to next semester, and I will be teaching that as well. So this reaction, I will tell you how it causes fire. Okay, it's really violent, and when you put the sodium metal in water, it goes boom, and then you get a cracking sound, and the fire, it can be really violent, so be very careful. So you can see here that this reaction is endothermic or exothermic. Is this reaction endothermic or exothermic? Exothermic, how do you know? Negative delta H, right? That's correct. So you can see that the phases of all the substance, well, we've got sodium as a solid, we've got water as a liquid, we've got NaOH as the aqueous solution. And here we get the hydrogen gas, right? So let's take a look. So if we basically assume negligible changes on liquids and solids volume, basically they don't change a lot anyway. So the volume change of the system depends only on the gas, right? And because of that, if you have reactions containing gases, we can calculate the relationship between delta H and delta E as follows. Well, I think this is for your subject. Delta U, I mean, it's actually delta E in our context, right? So let's change all these delta U to delta E, but they're the same thing anyway. In some textbook, they are written as delta U. In some textbook, especially in Chang's, which is our textbook, it's written as delta E. Okay? So these two are the same thing, which means the change in internal energy. Okay? So you can see from definition that was from the previous lecture. So if you still confused how did I get this equation, go back to review the previous lecture. Okay? So delta H equals delta E plus P delta B, right? That's the definition of delta H by the way, under constant pressure. Okay? But if you have a reaction that contains gas and only gas contributes in the volume change, so for ideal gas equation, P delta V becomes delta N times RT, and this delta N comes back again. This delta N is essentially the same as the one that we talked about in the previous chapter, right? This delta N is total number of moles of the products. Subtract with the sum of the number of moles of the coefficient. Oh no, sorry, reactants, my bad. So basically you take the sum of the stoichiometric coefficients from the product side and then subtract with the sum of the stoichiometric coefficient on the reactant side. But in this, we only count gases. Right? You only count the gases, not the liquid, not the solid, not the aqueous solution, just gases. Okay? So, why? Because we assume that only gas contributes to the change in volume, right? So that we can relate P delta V to delta N times RT using the ideal gas equation, which of course does not apply for liquids or solids, right? So, if you take a look at this equation, can you tell me what's my delta N in this context? Take a look at this equation right here. What's delta N? Keep in mind that for this part, we only count gases. What's delta N? So how many moles of gases are there on the product side? 2? Really? Just 1, right? Only hydrogen, right? Just the gas. What about on the reactants side? How many moles? 0, nothing, right? So it's 1 minus 0. Delta N in this problem is 1. Okay? So, take a look here. Now that I plug everything here, delta E is delta H subtract with delta N times RT, right? So this is delta H supplied by the chemical equation right here, and we've got 1 mole, which is our delta N, okay? And then we've got R, which is, well, I use the thermodynamics unit first, which is in kilojoules per moles per Kelvin. So there are 2 values of R to keep in mind. One of them you may be more familiar, it's 0.0821. But keep a look at the unit. Here it has the unit of liter atmosphere per mole per Kelvin, right? But the value of R that we always use in thermodynamics, we don't really use this. We use this 8.314 joules per moles per Kelvin, right? So these are the 2 values of R. They are the same thing, but only with different units, right? And if you notice here in this problem, I convert 8.314 further into kilojoules per mole, right? So that's why I multiply this with 10 to the negative minus 3 right here. So why do I choose this value of R to calculate? Well, you can see that quite clearly because you can see here that the delta H supplied by the problem has the unit of what? Kilojoules per mole, right? So when I do this calculation, the units are important. So I have to choose something that has similar unit to some other values provided by the problem, right? So you can see here that the problem supplies delta H in kilojoules per mole, then I should not really use this R because the unit of R is not in joules. I would rather use this one, right? To make the unit be able to add up together, right? So you can add up the values together due to be in the same unit, right? Because otherwise you can't just add them together. So this is very important too. I hope you learn that from Ajahn part because when you do this kind of calculation, the number one thing that you get wrong all the time is wrong unit. Okay, so be careful with all the units. Always take a look on the values and the units, okay, and see what kind of conversion you should take. That's very important in calculations. Okay, so keep that in mind. So, okay, I ramble too much. Let's go back to our lecture. Okay, so we've got one mole right here, and this is R in kilojoules per moles per Kelvin. And of course, the temperature is in Kelvin. In thermodynamics, you only use the temperature in Kelvin, just like in the previous chapter. Okay, the same thing. So when I do all this calculation, this is what I got. I got it to be minus 370.0 kilojoules per mole. So you can see that, well, this is my delta E minus 370, but my delta F is minus 367. Do they differ a lot? Not really, right? Just only 3 kilojoules per mole, just about 1% difference, right? So basically, delta H and delta E of the reaction doesn't really differ a lot, right? It really depends on the context. Well, let's see, if you want to insist that you want to use this value of R, can you do it? Yes, you can, but you need to have some other conversion factors for energy, right? So that adds up the complexity of your problems. So I would recommend that. But here you are. I changed this because I need to cancel the liters per atmosphere to joules. When I do this kind of conversion, this is what I get, right? So in thermodynamics chapter, I would strongly recommend that you use the R value in the SI unit, which is 8.314 joules per moles per Kelvin, right? Only in chapters regarding thermodynamics. But in other chapters, feel free to use this, it's easier. But in this chapter, you will typically use this R because you're dealing with energies in joules, right? So use that when you see energies in joules involved in the problem, okay? If you see that is the case, you will almost always need to use this value of R, okay? So be very careful with the units. Alright, that's my warning. I warned you. Okay. Any questions before we move on? Alright, let's move on to the next slide. Now, here is the example. I give you 5 minutes for the calculation. Okay, now is 8:19, so we have until 8:24. Okay, many of you got the answer? Maybe not. Well, this problem may trick you. So basically, you have to see what I put in bold right here. The keyword here is per 4 moles of CO, and then you have to look at this unit of delta H right here, right? So basically, this value of delta H is per how many moles of CO? Just 2, but the problem explicitly states that we have 4 moles, not 2. So what is going to be my delta H for 4 moles of CO? So I have to multiply this number by 2 to get that number, right, per 4 mole, right, because there are 2 times more CO than in the balance equation, right? So basically, delta H per 4 mole of CO is going to be minus 1132 kilojoules. Note that I get rid of per mole part of the unit, because I explicitly say that it's per 4 moles of CO is no longer per mole of a reaction, right? So that's why I just use this unit, no longer per mole, just kilojoules. Okay? So now let's take a look at delta N. So what's my delta N? What do you think? Is it going to be minus 1? Do you think so? Do you think it's going to be minus 1? It's actually not minus 1. It's minus 2. Why? The keyword is here because we double everything, right? Instead of having 2 moles of CO, we have 4 according to the problem. So for the product, we don't just get 2 moles of CO, we got 4. So this has to react with 2 moles of oxygen, right? So in actual reaction, we actually have this happen. Right? This is the actual thing that happens according to this problem. Right? So delta N, according to the actual condition of this problem, is going to be minus 2. Okay? So delta E is going to be delta H minus delta N times RT, right? So now I'll plug everything in. It's going to be minus 1132 kilojoules on the delta H part minus 2 times 8.314 times 10 to the minus 3 kilojoules per moles per Kelvin times the temperature, which is 298.15 Kelvin. So you can see here, this minus 2 is minus 2 mole. So this guy goes away, right? And the Kelvin goes away. So we have kilojoules here, and we also have kilojoules here. So what's going to be my answer? Just run the calculator. What's going to be the answer for this problem? Let's see. Okay, so my answer is minus 1127 kilojoules. Okay, that's my answer. So, still, it's not that different. But the only thing that might get you wrong here is you put in minus 1 instead of minus 2 here. So be careful to read the problem because maybe the problem gives you a clue. Okay? So you always need to be on lookout for the clues in your problems. Okay? Like in this case, well, I supply the balance equation right here, but I don't just ask you directly. I just change the problem a bit to 4 moles of CO. So be careful for the questions. Okay? Always look out for the clues. Okay? Any questions? Alright, let's move on. Now, another example. Which of the following processes has the smallest difference between delta E and delta H, given the number of moles of water is the same for all cases? Well, I give you just 1 minute to think. This question doesn't have any calculation. It's purely conceptual. Okay? Just 1 minute. Think carefully, and then I'll ask for your answer. Okay? Okay, any of you get the answer? What do you think? Is it A, B, or C? Who think it's A? Raise your hand. Who think it's A? Anyone think it's B? Anyone think it's C? Well, the correct answer is A. That's correct. Why is it A? Can anyone tell me why A? So it's this one. It's correct. Why? Just guess it? well, just look at what I wrote right here, right? This is the definition of delta H. Delta H is delta E plus P delta V, right? So the differences between delta E and delta H is only this term, right? P delta V. So if the differences between delta H and delta E is to be very small, it would imply that P delta V needs to be very small as well, right? And for P delta V to be small, our delta V needs to be small too, right? So you can see that in A, it involves the change of the phase from ice into liquid. So when you go from ice to liquid, imagine the volume doesn't really change a lot, right? So the change of volume is quite small. But if you notice in B or C, both changes into what? Gases. And gases occupy so much volume compared to liquid and solid, right? So the volume change in B and C will be much, much greater than A, and that will result in higher difference between delta H and delta E for both B and C. So that's why the answer is A. So you guys are correct. No matter what the reasons are, that's correct. Okay? But the actual reason is what I just said here. Okay? Any questions? Okay. Let's move on. Okay, before we go into another topic, let's talk a little bit about telemetry. Okay? Of course, you guys all did this experiment last week in the laboratory. Okay? You had calorimeter. So the purpose of this subject, calorimetry, is only for one thing. You want to measure the heat. Okay? So the principles are quite simple when you want to calculate the heat. Okay? If you want to compute the heat absorbed or released by any object, that is computed from the product of an object's heat capacity with the change of temperature. Okay? So basically, that will always be our definition for heat. heat is always equal the heat capacity, or C, times the change in temperature, right? And the typical units of heat is in the units of energy, right? So what are the units of energy? Heat can be in joules, in calorie, anything, etc. that are energy units, right? So basically, let's say if our heat is in joules, so the unit of heat capacity is essentially joules per Kelvin or joules per degree Celsius, because the scale of Kelvin and degree Celsius is the same, right? And delta T can be either in Kelvin or degree Celsius. In this rare instance, in thermodynamics, that you use degree Celsius, okay? But otherwise, don't use degree Celsius, okay? So that's the main definition of heat. And we want to focus on this particular thing, which is C. So how do we get C for any objects or matters? Okay? If the object is just one substance, one pure substance, like water or anything like that, the heat capacity of that is going to be the product between mass and the specific heat capacity, which we typically use the symbol S. Okay, you saw that in your laboratory experiment as well. And the unit of this specific heat is normally in the unit of energy per mass, right? In your case, in your experiment, S of water is equal to 4.184 joules per grams of water, right? So you can see that the specific heat has the unit of energy per mass, okay? And that's why when you calculate the heat absorbed or released by a substance, you can just use Q equals Ms delta T, okay? Because our Ms is just one iteration of the heat capacity, okay? But for calorimeter, it's not really one pure substance, so you have to find some value in your experiment, right? You have to find just a single value of C for that thing, okay? So, how do you calculate heat of chemical reactions? Okay, well, you can do it in two ways. You can try to calculate the heat in the constant volume settings or under a constant pressure settings. What you did in the experiment in the previous week was under the constant pressure settings. Okay, but let's take a look on how you do that in the constant volume settings. It's a little more complicated than the constant pressure settings, right? Because in the constant pressure settings, we can just assume that in the laboratory that you are performing experiment, or even right here, the air pressure pretty much remains the same, right? But it's really hard to keep the volume constant. So what they did here is use something called the bomb, right? So it's spelled the same as the bomb that explodes, boom. But this is not the bomb that explodes. It's actually the bomb that is used to keep the volume constant, right? How so? So you can see that we have the sample. Let me zoom in a little bit. So if you take a look at this photo right here, this thing is called a bomb, right? And inside a bomb, you have something that is called a sample cup. So basically, you have the sample and you want to heat things in here, right? And inside everything, we have the calorimeter with the water surrounding the bomb, right? So the thing that happens here is that the volume is kept constant. The bomb may change in volume due to the heat inside, but you can see here that you have another layer of the actual calorimeter bucket that actually doesn't change in volume. And we normally consider everything in here to be a system so that we can keep the system under constant volume. Okay? So the mechanism is a little bit we did all these purpose to keep the volume constant. Okay? So, when you calculate the heat of the reactions, right? Of course, you place the sample in the bomb, and then you compute the heat of combustion of things inside the bomb by calculating the heat that the water that surrounds the bomb gain, right? So basically, when you perform some reaction, and let's hope that it releases heat. So when this thing releases heat, the water that surrounds the bomb will get all those heat and increase in temperature, right? So you can calculate the heat of the reaction that goes on inside the bomb by just calculate the heat that the water gains, right? But not only that, since we treat the whole thing as a calorimeter, we need to also assume that there will be some heat lost into the calorimeter as well, just like you did in your experiment, right? So basically, you can see that Q of the system, because we consider everything here, right? The calorimeter plus the bomb is going to be Q of the calorimeter plus Q of the reaction. So, but we treat the whole box as an isolated system, right? So nothing comes in or out, just like in your experiment. So Q system is 0 because we treat it as the isolated system. So if that's the case, Q of the calorimeter is minus Q of the reaction. And that is simply equal to C of the calorimeter times delta T of water. Okay? Let's take a look. Now we have the constant pressure calorimeter, same thing. This is actually the one that you did. So instead of in this image that uses the styrofoam cup, you use the double wall glass tubes. Same thing, same kind of idea, right? You only need to perform your reaction inside an insulated container. In your case, the double wall glass tube in your experiment. Okay? And we assume that the water plus container is an isolated system. So the principle is the same, right? So Q that the reaction loses is the Q that the calorimeter gains, right? That's like when you calculate the C of the calorimeter when you mix in hot and cold water, same kind of idea, right? So when the hot water loses heat, the cold water plus the calorimeter gains heat. So it's the same kind of principle. The heat doesn't escape the system due to being an isolated system. But if you just perform the reaction right away and put everything inside the calorimeter at the same time, Q of the calorimeter will be just minus Q of the reaction because we don't put cold water inside the calorimeter first like you did in the experiment. If you put everything in, it's going to be just Q calorimeter equals to minus Q reaction. Okay? So you have to look carefully what's in and what's not in the calorimeter. Okay? But same kind of principle. So let's take a look here. A 1.45435 grams sample of naphthalene was burned in a constant volume bomb calorimeter, and the temperature of the water surrounding the bomb rose from 20.28 to 25.95 degrees Celsius. If the heat capacity of the bomb and water is 10 plus 70 kilojoules per degree C, I want you to find the molar heat of combustion of naphthalene. Okay? So I give you 5 minutes to do this problem. I mean, the principle is the same, but the thing is, you just perform the entire reaction inside the bomb. You don't put everything first. So basically, the temperature rise minus Q reaction will be just Q of the calorimeter. Okay? So that's the answer. So you take a look at this problem right here. So of course Q of the reaction is Q of the minus Q of the calorimeter plus water in the case of the bottom. Okay? So Q here is just C times delta T, right? So we've got 10.70 kilojoules per degree Celsius as our C. And the temperature of water changes is 25.95, which is the final temperature, minus the initial temperature, which is 20.28 degrees C. So if I work out that number, so don't forget the minus sign right here, Q of the actual reaction is going to be minus 57.66 kilojoules. Okay? So if I want to compute the molar heat of combustion, so that's per 1 mole of naphthalene, right? This is not per 1 mole, it's just per how many grams? Just this guy, right? So I have to find the number of moles of naphthalene by dividing that with the molecular weight, which is about 128. So we have 0.011 moles of naphthalene in our sample. So if I divide this number by the number of moles of naphthalene, here I got minus 5,242 kilojoules per mole, right? This number sort of makes sense because why? For methane, it's kind of highly exothermic, already about minus 300, 400 something kilojoules per mole, and that's just one carbon atom molecule, right? Now this molecule has 10 carbon. So it releases a lot of heat per 1 mole of that. Okay? Well, the second question here, is this the same as the change in enthalpy? Well, sorry, this is not delta H. This is, I would say, this is delta E. It's not actually the same as enthalpy. Why? Because we perform this experiment in bomb calorimeter, which means we keep the volume constant. But enthalpy change only applies when the volume is, no, not the volume, the pressure is constant, right? Enthalpy change is defined only when the pressure is constant, not when the volume is constant, right? If you recall the first slide that I gave you, heat of a constant volume process is delta E, but heat of a constant pressure process is delta H, right? So this is not the same as enthalpy, but it might be quite close, okay? So that's this problem right here. I think I have another problem here. So another 5 minutes. Okay, anyone who got the answer? It's easy. Yes, it is. It's easy. So, how did I do this problem? So you can see that this is what the problem says, right? 26.27 grams of lead pellet with the temperature of 89.98 degrees Celsius was dropped into a constant pressure calorimeter of negligible heat capacity. Negligible heat capacity, it means that do we consider the heat capacity of the calorimeter? No, right? Because the problem says it's negligible, so we don't consider it, right? We only then consider the heat of water. So basically, the heat of lead cooling needs to be the same as minus heat of the calorimeter plus water, right? So we use the same kind of relationship that you did in the experiment last week. That's the same thing, right? So, what is the heat of lead cooling? So it's the mass of lead times the specific heat of lead, which I don't know for the moment, so I just put that as an unknown, just right there, times the change in temperature, which is T final minus T initial. This thing is cooled to 23.17 degrees Celsius. So this is T final, and this is my T initial right here. So that's the heat of lead cooling. It's going to be a negative value. I don't mind because my initial initial equation is already correct. So let's take a look at the right hand side. Minus Q of the calorimeter plus water. So I still have my minus sign right here. Times what? Mass of water. 100 milliliters, just 100 grams of water. Right? Because we assume that water is 1 grams per milliliter. Okay? Just like you did in your experiment. Times what? This is the specific heat of water. You also know that value from your experiment, right? 4.184 joules per grams per degree Celsius. And then delta T of water, which is T final, 23.17 degrees Celsius minus 22.50 degrees Celsius. So you only have to solve this equation. And of course, I don't solve it myself. I use a computer. But in the exam, you need to do it by hand. So it's still not that difficult to solve, right? Just be careful. But if you solve it correctly, this is what you should get. The specific heat of lead is 0.159 joules per grams per degree Celsius. Okay? So before we move on, I want you to take a look right here. This is S of water, 4.814 joules per grams per degree C. But for lead, it's just 0.1. The difference is about 40 times. That's quite a lot, right? So the heat capacity of metal is normally much less than liquids, right? They are things like water. Why? The heat capacity of metal is much less than water. Why? When you think of metals, what do you think of their properties? The properties of metal, they conduct heat, right? Metals, they conduct heat and electricity, right? Since metals are good heat conductors, so they gain heat easily and also lose heat very easily as well because they are such a good conductor of heat, right? And because of that, they just let heat pass away without keeping heat in itself. So heat capacity means the capacity of that material to keep the heat inside. So for metals, since they are good conductors, they don't want to keep the heat inside them for long. That's why metals normally have low specific heat, right? But what about water? Is water a good heat conductor? Not really, right? So since water is not a good heat conductor, so when water gets heat, it just keeps the heat inside itself rather than pass the heat somewhere else like metals do, right? So that's why the heat capacity, the specific heat of water per the same amount of mass is much higher than in metal, right? So there's an explanation for that. Okay? Any questions? Alright. So let's move on. So for calorimetry, the equations themselves is quite straightforward. Q equals ms delta T or C delta T. The only thing that you get wrong is the signs and how you define the system. That's going to be the key area that you need to work on. Okay? So be very careful with those. Okay? Now, let's talk about what we call Hence's law. Okay? Let's suppose you'd like to know the enthalpy change of some reaction, but somehow you don't have access to A and B. So you don't really want to perform this experiment and know because you don't have A and B to actually do the experiment. But wait, you go and consult your books or your research articles, and then you know that, oh, this is what I know. I know the delta H of this reaction and the delta H of this reaction. So what happens if I add these two reactions? Bingo! I get the reactions that I actually want to study, right? So the Hence's law states that the delta H of this reaction is just the sum of these two little guys, right? Why can we do that? We can do that because enthalpy or H is a state function, right? What is a state function, by the way? A state function is a thermodynamic variable that the difference between the final and the initial states do not depend on any pathways, right? So basically, let's say this is the initial, this is the final, right? So I want to calculate the change of enthalpy from the final with respect to the initial phase. I don't know the path, but let's take a look at these two guys. If we add these two reactions, we get the same path. We get some path from the initial to the final state, right? And since it's independent of the pathways, so we can say, oh, if we add this, I know for sure it's going to be delta H of my final reaction because of the concept of path independence of the state functions. Okay, so I can take any sub-reactions, 2, 3, 4, 5 reactions, how many, whatever I prefer, right? Add them together, and then if I get the same final reaction that I desire, the final delta H will be the sum of all those little reactions right there. That's Hence's law for you. Okay, we can do that because enthalpy is a state function. So I can take any pathways, any steps that you prefer, as long as I get the same final reaction. The delta H that works out is going to always be the same. Okay? So let's take a look at the Hence's law in action. Well, you saw that in the previous experiment too, when you calculate the heat of dissociation of acetic acid in your laboratory. Okay, it's the same kind of concept right there. So let's take a look at this. You have this reaction here, but if I add them together, this is the net reaction that I prefer. So my delta H of my final reaction that I want to find is going to be the sum of these two guys. Okay? So it's either in one step, many steps, 2, 3, 4, 5, as long as I have the same final outcome, my delta H of this reaction will always be the same due to H being a state function. Okay? Which implies the concept of path independence. Okay? So that's Hence's law. How do we use Hence's law? We normally use it in what we call the standard enthalpy of formation. Okay? So this concept is very important. It might come up a lot on your exam too, so pay attention. What is this? This thing normally has the symbol delta H naught F. This symbol right here is not called circle or anything. We pronounce it naught, N-A-U-G-H-T. We don't call it delta H0 or anything. We call it delta H naught. Okay? So this thing, we call it delta H naught F, where this subscript F denotes formation. And this naught denotes what we call a standard, right? So what does it mean to be a standard? So what does the word standard mean in this context? Well, it means that it is the enthalpy change at the standard state. Well, what is the standard state? It means that 1 mole of compound, right? And then what? 25 degrees C, 1 atmosphere of pressure, right? That's a very important concept. The standard state, well, not necessarily 1 mole, sorry, but it has to be 25 degrees C and 1 atmosphere. That's the standard state for you, 25 degrees C and 1 atmosphere, right? Of what we call the formation reaction. This is a very important concept. So what is the formation reaction? Let's take a look here. If I want to calculate the standard enthalpy of formation of, let's say, carbon monoxide, okay, CO. So the way I write the formation reaction is like this, okay? So in order to write formation reactions, so I have to list each element of the compound that I target. In this case, CO, right? So how many elements are there in CO? There are 2 of them, right? Carbon and oxygen, right? So I have to write out carbon here on the right-hand side and also oxygen. But wait, carbon, why did I write just C and oxygen O2? The trick is right here, so pay attention very well. Since the standard state is 25 degrees C and 1 atmosphere, right? So you have to write the allotropes or the form of that particular element that actually exists at this condition, right? So for example, oxygen at this condition, it does not exist as a gas with just 1 atom. It exists as O2, not just O, right? And not just exists as a molecule, O2, it also exists as a gas under this condition, right? What about carbon? Carbon exists as graphite, a solid, right there, right? So we write this equation, carbon in the graphite form plus 1/2 O2 gas goes into 1 mole of CO in the gas phase. Notice that the CO state needs to correspond to the standard state as well. And in the standard state, CO is a gas, right? So you can see that this is the enthalpy of formation of CO is minus 110.5 kilojoules per mole. Note that this is always per 1 mole of the compound that you look for, always, right? And when you write the formation reaction, you need to break the compound down into elements, right? That's actually one thing also that we need to take note. The standard enthalpy of formation of an element in the standard state will always be 0 by definition. Let me ask you this. What is the delta H naught F of, let's see, Cl2 gas? It is 0 by definition. Why? Because Cl2 contains only chlorine, right? It's just an element chlorine. And is this the form of element chlorine that exists at 25 degrees C and 1 atmosphere? Of course, yes, right? Because chlorine does not exist as monatomic or just one atom chlorine. It exists as a molecule, Cl2, at 25 degrees C and 1 atmosphere, and also as a gas. So this is a form that represents the elemental chlorine at the standard state, and by definition, the heat of formation or delta H naught F of this has to be 0. That's the example right there, right? What about delta H naught F of liquid mercury? Is it 0 as well? Delta H naught F of liquid mercury, is it also 0 as well? Yes? Why? Because mercury at 25 degrees C and 1 atmosphere is a liquid, right? That's why it's 0, because that represents the elemental form of mercury at the standard state. Now, something more tricky. Is the heat of formation of solid mercury 0? It's not. Why? Because at standard state, mercury is not a solid, right? Elemental mercury is not a solid. So that's the idea. Okay? And this is the idea that people normally get confused a lot. So I really want to clear that up. Okay? So you should know this. If you're still confused, rewatch the video of this lecture, or if you're still confused, ask me. Okay. So this is a table of the heat of formation of many compounds. So you have to pay attention to all those zeros, right? So those are all the elemental forms that represents that element at the standard state, right? You can see something like this. For mercury, liquid is 0 because at 25 degrees C and 1 atmosphere, mercury is a liquid, right? And for nitrogen, it's 0 for the form of N2, gas, etc., right? But for anything else that are compound, they are not 0 by definition. And if you are to write the formation reaction, you also do the same thing as what we did for the previous slide. Like for example, for CO, it's just per 1 mole only. So you can have 1/2 right here. It's fine because we define this only for 1 mole of the compound, right? That's the definition. That's why we have to keep 1/2 right here. Okay? And we can use the standard heat of formation of each compound to calculate the standard enthalpy change. This thing, delta H naught, has the name of the standard enthalpy change. Right? So the standard is denoted here by the naught, right? We can also call this delta H naught, which means the standard enthalpy change of the chemical reactions. Okay? So let's consider this reaction. AA plus BB goes to CC plus DD. Given that you know the standard heat of formation of all compounds A, B, C, and D, then you have this balance equation and you can easily compute the standard enthalpy change of your reaction by just simply use this formula right here. So what does that mean? So it means that if you want to calculate the standard enthalpy change for your reaction, well, take the products first. So you have this stoichiometric coefficient of C times the heat of formation of C, plus the stoichiometric coefficient of D times the heat of formation of D. So that's the contribution from the product side, and then you subtract that with the contributions from the reactants side, right? Same thing. You have the stoichiometric coefficient of A times the heat of formation of A, right? plus the stoichiometric coefficient of B times the heat of formation of B. So that's the rule right here. So if you compute all these values carefully, you get the standard enthalpy change for your reaction. Okay? It's easy. Since it's that easy, and normally you can just look at the values of these things from the table like this. So it's easy, right? So you can consult this table for all those values. Okay? Now, let's take a look. I want you to calculate the standard enthalpy formation of C2H2 given all these. Well, this is actually the demonstration of Hess's law too. So let's see how many slides do I have. Okay, not that many. I give you 5 minutes for this one. Here's the answer. So, to do this, you need to write down the formation reaction of C2H2 to get the idea, right? So this is the formation reaction of C2H2 is 2C graphite plus H2 gas goes to 1 mole of C2H2. This is what I need to calculate delta H naught F of C2H2. But look, I have some weird reactions right here. So how do I get my delta H naught F of C2H2? Well, you have to think about it carefully. You have to use Hess's law. So you want some reaction to add up to get to that reaction that I box it, right? So let's say the first step, I take equation 3, which is this one, right? Reverse it and then reverse it and then divide by 2. So that's 2 steps. So I reverse this reaction and then divide this reaction by 2. So I get 2CO2 plus H2O goes to 1 mole of C2H2 plus 5 halves of O2, right? And when I reverse the reaction, I have to flip the sign of delta H as well. And as I divide that by 2, I have to also divide the O delta H by 2 as well, because we have less substance, so we have less heat coming in or out, right? So for step 1, delta H of the reverse and divided reaction, that's minus 1299.4 kilojoules, just kilojoules, okay? And step 2, I multiply the first equation by 2 because I want to get rid of CO2 from here to get to CO2 that eventually will cancel, right? So the new delta H after multiplied by 2, that's minus 787 kilojoules, right? And I don't need to make any change for 2. I just use 2 plus 4 plus 5, and if you do that, I'll get the final equation right here. Okay? So, if you add up the number, so that's minus 285 and with 1299 and 787, then my number should be about minus 2300, something like that. That's my heat of formation of acetylene or C2H2. Well, let's take a look at the table whether I get my correct number. So for acetylene, C2H2, well, no, it's not in this table. Let me check on Google. Well, the heat of formation of acetylene is, let's see. Yep, about right. Okay. Well, sorry, this is not minus, it's plus. I have to flip the sign. This thing is minus. Okay? So if you add up those numbers, it's about 228.31. Sorry about that. This is not minus, this is plus. Okay? Because I flipped this, so I have to flip the sign of this guy as well. Sorry about that. So it's plus 1299.4 minus 787 minus 285. And then we work out that number correctly. Well, you should get about 220 something kilojoules per mole in line with the values you see from the internet. Right? Okay. The last problem here, I want you to calculate the enthalpy change of the standard state of the thermic reaction using the data from the table. Well, since we are running out of time, so let's just follow along, right? So you can use the tabulated data to calculate the standard enthalpy change of this reaction, right? Which is just take the products first, well, 2 times delta H naught F of iron liquid plus delta H naught F of Al2O3 in the solid phase. So that's from your product, and then subtract with delta H naught F of Fe2O3 solid plus 2 times delta H not F of aluminum solid. Well, that's 1 0 heat of formation right there. Which one? That's 1 0 heat of formation right there in that equation. From which one? Guess it. So which of these four things has 0 standard heat of formation? Guess it. Which of these four things has 0 standard heat of formation? Which one is the representative form of its element at 25 degrees C and 1 atmosphere? Should be aluminum, right? Because it's the metal at 25 degrees C. So this thing is 0, I know for sure. And for the rest, just consult the table. Okay? Well, what about for iron? Well, maybe they didn't provide it. Maybe you can search the internet. Sorry about that. So you can search the internet for the heat of formation of iron. That should be it. And then for Al2O3, well, you can take this value right here. And for Fe2O3, well, not also supplied. But if you have your textbook, I mean, you should have delta H not F for all these things. And then you plug these into this equation right here, and then calculate, and then you'll get the answer. Okay? So that's basically how you use the standard heat of formation. Okay? In the calculation of the standard enthalpy change of your reaction. So go back to the video, which I will provide after this course for more details. Okay? Last but not least, for today, to calculate the heat of the solution. I mean, I won't put this on the exam, but you should know. So if I want to calculate the heat of the solution, is the heat the system either release or absorb to dissociate these ionic compounds to become the solvated ions, right? So basically when you dissolve ionic compounds, so the ions will be surrounded by water, right? So basically if you want to calculate the energy of this process, maybe you can calculate it directly, right? But what you can do is you can take some other step and use the concept of Hess's law. So basically you can calculate the energy that it takes to melt all these solids and break them apart into the ions in the gas phase. That's the first step. And then you can calculate the energy it takes for water to solvate these ions in the solution phase, right? So if you add the energies it takes for these two steps, it will be the same as the energy of this thing that we want to find, right? Due to Hess's law, due to the property of enthalpy, that is a state function. So I don't know exactly what the energy of this pathway is. I take another path and say, oh, the sum of the energy of the other path must be the same as the one that I'm interested in, due to enthalpy being a state function. Okay? So that's why the concept of the state function is very, very, very important in thermodynamics, I warn you. So go back and read those concepts and try to get yourself understand why Hess's law is like that. Okay? Alright, I guess we are running out of time. So I think that's it for today. If you have any questions regarding today's lecture, feel free to ask me, okay? And then I'll see you guys again for lecture 5 on Monday. Okay, so have a good weekend and I'll see you guys on Monday. No, not Monday, sorry. Today's Monday. My bad. Thursday. Okay. And Thursday will be our last lecture before the midterm. Because next week there's no lecture. Okay? So that will be our last lecture before the midterm. And we'll tell you what I will have on the midterm on Thursday. Okay? I'll see you guys on Thursday.
Thanks.